Today we're going to continue looking at section 4.4, exponential and logarithmic equations. So today we are going to use logarithms to solve exponential equations. We're going to use the definition of a logarithm to solve logarithmic equations. And we're going to use the one-to-one property of logs to solve log equations. All right, so a logarithmic equation is an equation containing a variable in a logarithmic expression. So something like log base 4 of x plus 3 equals 2. So the x is inside that expression. Notice that another one would be if we have the natural log. So we've got, the natural log of x plus 2 minus the natural log of 4x plus 3 equals the natural log of 1 over x. Okay, so something along these lines would be equations in logarithmic form. Okay, so using the definition of a log to solve these equations. First step, we want to try to get the equation in the form log base b of m equals c. Okay, so that means that we have one log on one side isolated by itself. Okay, once we have it in this term or in this form, we're going to use the definition of what a log is. Remember, logs are exponents, so we are actually going to rewrite this into an exponential equation. So it starts as log base b of m equals c, but it'll then turn into b raised to the power of c equals m. All right, because once we have it into the exponential form, now we're going to be able to do what we did in our last video. Okay, we'll be able to either maybe get the same base on both sides, or we'll take the natural log of both sides in order to then start solving for the variable. But now here's the thing. When we're talking about logs, we've got a restriction on our domain. So that means we are going to have to make sure that the answer that we get fits within the domain. So step number 4 says we have to check the proposed solution in the original equation. And this includes the solution set to only have values for which m is greater than 0. So we have to plug it into that original equation, and if the expression that is connected to the log is greater than 0, then we know that our answer checks out. If it's something that equals 0 or is less than 0, we know that that cannot be a solution because it doesn't fit within our domain. All right, so let's take a look at this example. We are going to solve log base 2 of x minus 4 equals 3. So notice that we have the log isolated by itself. Every number is inside the parenthesis. The 4 is inside. So since there's nothing outside or not connected to the log, we don't have to worry about isolating it. So because we have the log isolated to one side, we are going to rearrange this and rewrite it into exponential form. Okay, so remember, I identified the base. It's going to be raised to what that log equals. So it equals 3. So it's 2 to the third power, and that's going to equal the x minus 4. Okay, so we start with the base, we loop around to write our exponential form. All right, now that we've gotten rid of the word log, because we rewrote it as an exponent, we can go ahead and we can solve for x. 2 to the third power is 8. And we'll have to add 4 over to the other side, and we get that x equals 12. Now, once again, I cannot just circle this and say that that's my answer until I've checked it out. So I need to go back to the original problem, log base 2 of 12 minus 4. I don't really have to verify that it equals 3, but what I have to check is that what I have inside here, the expression that's connected to the log, it needs to end up being greater than 0 in order to be a solution. Well, notice that 12 minus 4 is going to be greater than 0, so that means that 12 is our solution. Okay, if it wasn't, then we would say that we have no solution because the only value for x that we got didn't work. Okay, but in this case it does, so 12 is our answer. Okay, let's take a look at this next one. We have 4 times the natural log of 3x equals 8. Notice that this time we do not have that log isolated by itself. There is a 4 out in front. So since 4 is being multiplied, I am going to undo multiplication by dividing both sides by 4. So now we'll have the natural log of 3x, and this is going to equal 2. So now don't forget, natural log is the same thing as log base e. So I am going to be able now, since I have the log isolated by itself, to rewrite this into exponential form. So since the base is e, it's going to be e squared to equal 3x. What I'm going to do then to get x by itself is I'm going to divide both sides by 3, and then we're going to have this answer. So it's e squared divided by 3, which let's approximate it. So we'll use our calculator. Let's round to 2 decimal places, and notice that we'll get approximately 2.46. Now, once again, because my original problem is a log equation, there's restrictions on our domain. So I'm going to check to make sure that this is legit. So we'll have 4 times the natural log, and now it's 3 times 2.46, and that's going to equal 8. Once again, we really just have to check that what we have, the expression connected to the log, is going to be greater than 0. We'll notice that 3 times 2.46 is going to be a positive number, making it greater than 0. It checks out, so we can say that this is our solution. Let's take a look at this one. We've got log of x plus log of x minus 3 equals 1. Notice that this time we do not have one single log isolated by itself. There are 2 logs in this problem. And this is why it's super important that we know our rules for condensing. Because these logs share the same base, and I have an addition sign in between them, we can follow the rules and we can condense it down to a single log. Remember, when it's addition, this is really the product rule, which means I'm going to multiply the expressions. So I keep the log, but then it's really x times x minus 3. That's going to equal 1. Okay, so now I do have a single log on one side. Remember, this is technically base 10 if I don't see a base. So now I get to rewrite this into exponential form. So 10 is my base. I'm going to go around. 1 is my exponent. That equals x times x minus 3. Got to start solving for x, so I'm going to distribute that. 10 to the first power is just 10. X times x is x squared. X times negative 3 is negative 3x. Because this equation contains an x squared, an x, and a number, I do want to think about solving a quadratic by maybe factoring. So I got to get everything over to one side. So I'm going to subtract the 10 because I want to keep that x squared positive. So we'll have 0 equals x squared minus 3x minus 10. And this is definitely factorable because there's a 1 in front of the x squared. We're asking ourselves what multiplies to the last number but adds to the number in the middle. So we're going to have then x minus 5 times x plus 2. I get to set each of those factors equal to 0. And so that means I'm adding the 5. And so one of my potential answers is x equals 5. I'm subtracting the 2. And so another potential answer is that x equals negative 2. But remember, they're only potential answers because we have to check. So notice that if I check the x equals 5, we'll have log of 5 plus log of 5 minus 3, and that equals 1. So notice that here, that is greater than 0. Here, this is also greater than 0. Those two check out, and that's what we're looking for. So x equals 5 is a solution. When I check the negative 2, we'll have log of negative 2 plus log of negative 2 minus 3 to equal 1. Notice that in both of these cases, we do not get it, okay? It is not greater than 0, and this one is not greater than 0. We need both of them to be greater than 0 for it to be a solution. So in this case, negative 2 just does not work, so we only have one answer. Okay, so go ahead, pause the video, see if you can solve this equation. Okay, it was just like our last example. We have two logs, but they share the same base. So remember, we can condense it down. It is the product rule there. Because I don't see a base, it's really base 10. So I went ahead and I wrote it into exponential form. Notice I distributed the 5x to the x minus 1. 10 squared is really 100. I got everything over to one side. Because it's a quadratic, I wanted to see if I could factor it. All of them had a GCF of 5, so I factored that out first, because remember, that's always your first step when factoring. So then I can find numbers that multiply to negative 20 but add to negative 1. That would be negative 5 and positive 4. I only need to set the factors that have an x equal to 0. So my GCF doesn't have an x. I don't have to worry about that. But x minus 5 equals 0, x plus 4 equals 0. That's why I got 5 and negative 4. Okay, once again, all you had to do, I did a little bit more work when we were doing our checking, but remember, because I took 5 times 5 and I got 25, that's greater than 0. 5 minus 1 is 4, that's greater than 0 right there. You didn't have to do the rest of that work. You could just say, yep, 5 works. But then notice that when I did negative 4, we got several negative values. I need to have something greater than 0, which is why we could not have negative 4. All right, let's talk about another type of equation. It says using the one-to-one property of logarithms to solve logarithmic equations. So express the equation in the form log base b of m equals log base b of n. So if we have two logs and no other numbers that were not connected to it. So it's a log on one side, it's a log on the other, they're isolated by themselves. As long as the base is the same, then what we can do is in step number 2, we can follow this one-to-one property, and we get to do it just like we did with our exponent equations. If the base is the same, I got to ignore the base and I got to write the exponents equal to each other. Well, here with logs, if the log bases are the same, we get to ignore those and we get to set just the expressions equal to each other. That allows us then to solve for the variable, but once again, logs have restrictions on our domains, so we need to make sure that both sides of our equations, whatever the expressions are, when we plug it back into the original problem, we get values that are greater than 0. So let's take a look at this example. It says solve the natural log of x minus 3 equals natural log of 7x minus 23 minus the natural log of x plus 1. So right now it doesn't quite fit the form that the last slide told us, because I want to have a single log on either side of the equation. But the nice thing about all of these being natural log is that on the right-hand side with subtraction, I can follow the quotient rule. So I'm going to leave the natural log of x minus 3 on the left, but on the right, I get to write this as the natural log, and then I want division. We'll put the 7x minus 23 in the numerator, and we'll put the x plus 1 in the denominator. So I do technically have a natural log on one side, one natural log on the other. Notice how there's no other numbers outside of the expressions. So that's enough information then to use that one-to-one property. I can just set the expressions equal to each other. Now, because the right-hand side is a fraction, what we can actually do to solve this is we can think of this as a proportion. I can put the left side over 1, and when we have a proportion, we cross multiply. So that means that the x minus 3 is going to get multiplied by the x plus 1. And that's going to equal the 1 getting multiplied by the 7x minus 23. Okay, so I'm going to distribute on the left. X times x is x squared. X times 1 is 1x. Negative 3 times x is negative 3x. Negative 3 times 1 is negative 3. On the right, distributing a 1 is still just going to leave me then with 7x minus 23. I'm going to then move everything to one side. Because there's only one x squared term, I'm going to leave everything on the left. So notice that we've got a couple of like terms to combine, but I also want to subtract the 7x. So there's 3 like terms there. I'm going to add the 23 over. So we should get x squared Let's see, x minus 3x minus 7x is going to give us a negative 9x. Let me fix that square. And then negative 3 plus 23 is going to be positive 20. And this is still an equation. It now equals 0. I can solve by factoring. Notice that I can find numbers that multiply to 20 but add to negative 9. That would be a negative 4 and a negative 5. I get to set each of those factors equal to 0. So I get to add 4 to both sides. I get to add 5 to both sides. So my potential answers is x equals 4 and x equals 5. But remember, they're only potential answers until I've checked. So I go back to the original problem. I'm going to substitute in 4 first. So 4 minus 3 equals the natural log of 7 times 4 minus 23 minus the natural log of 4 plus 1. So notice 4 minus 3, that is greater than 0, so that checks out. 7 times 4 is 28. 28 minus 23 is still greater than 0, so that checks out. 4 plus 1 greater than 0, that checks out. So x equals 4 is a solution. Now I'm going to do the same thing with the 5. We're going to have 5 minus 3 for the first expression. Second expression will 7 times 5 minus 23. And then in the third expression, we'll have 5 plus 1. Well, 5 minus 3, greater than 0, so that's good. 7 times 5 is 35. 35 minus 23, still greater than 0. 5 plus 1 is greater than 0. That checks out. So in this case, we actually have 2 answers. Once again, if none of the answers work, then you would say no solution. So go ahead, pause this video, and solve this equation. So notice that on the right, we had to condense it down because it was addition. I knew that I wanted to really multiply. Because the logs on both sides have the same base, I got to ignore the logs and focus on the expressions. So I distributed the 2 to the 2x plus 3. So that's why 5x plus 1 equals 4x plus 6. So I subtract 4x, I subtract 1. I got x to be equal to 5. Once again, notice that when I substitute 5 in, I got 26, which is greater than 0. I got 13, which is greater than 0. And then obviously, we didn't have anything to substitute into the last one. So everything was greater than 0, which is why it checks out. And 5 is our answer. Okay, so that is us now solving log equations. Once again, always make sure that you are checking your solution.